Hello everyone, I'm Shen Yufeng from Carnegie Mellon University. Today, I will present our research work exploring long-term dependencies for generating dynamic scene graph. A scene graph is a directed graph where each node represents a labeled object and each edge represents an inter-object relationship. Our task is to generate a scene graph for the video, where the scene graph will dynamically change across the frames, which is known as the dynamic scene graph generation task. Due to the occlusion and fast movement, the scene graph is usually hard to infer through the local temporal context. Therefore, in this work, we hypothesize that capturing the long-term dependencies is the key to dynamic scene graph generation. We propose to model two kinds of temporal dynamics, the temporal object consistency and the temporal relationship transition. The temporal object consistency states that the object will not suddenly appear or disappear. The temporal relationship transition models the relationship transition pattern for the underlying action. To model these two dynamics, we propose the dynamic scene graph detection transformer, DSD, which consists of three parts: cause tracking, object transformer, and a spatial temporal relationship transformer. The cause tracking uses the Hungarian matching algorithm to construct the object sequences for each video. The matching is based on the similarity of predicate label distribution, the feature from FastRCN, and the bounding box position. In the object transformer, each object will only attend other objects in the same sequence obtained by cause tracking. This sparse attention enables the model to capture longer dependencies with lower computational costs. The relationship transformer consists of the spatial transformer and the temporal transformer. The spatial transformer first aggregates the information inside each frame. In the temporal transformer, each relationship only attends to other relationships that share the subject and object in the same sequences obtained by cause tracking. We test our model on the action genome dataset and use required K as the evaluation metric. DSD achieves a significant improvement in scene graph classification task and required lower K for scene graph detection task, which is around 4 points. We further demonstrate the hypothetical best case of DSD where we use the ground truth tracking sequences. It shows the greater potential to model the long-term dependencies in dynamic scene graph generation task, and our cause tracking algorithm greatly reduces the gap towards this best case. Our ablation studies show that the combination for all components in our model achieve the best results, and modeling the short-term dependencies cannot obtain the same performance as modeling the long-term dependencies. So qualitative analysis, we found the DSD indeed brings the temporal object consistency and models the temporal relationship transition. Furthermore, we want to point out that DSD is beyond the majority voting of the predictions from FastRCN. In the following example, we can see that most of the FastRCN predictions of the object in this sequence is person, but DSD successfully recovers the correct object label blanket through modeling the long-term dependencies. To conclude, we successfully captured the long-term dependencies for dynamic scene graph generation task by generating long sequences through cause tracking and modeling two dynamics through object transformer and the relationship transformer, respectively. We achieved the SOTA performance on action genome dataset and showed a hypothetical best case for modeling long-term dependencies. This is all for my presentation. You can refer to the following link for our paper, code, and pre-trained models. Thank you for watching.